Thank you. I am embarrassed to admit in front of this audience that I don't speak Spanish, so I didn't understand a word of that other than Paxos, but thanks anyway. So my name is Heidi Howard. I'm a research fellow at the University of Cambridge, and I've been fascinated by the problem of distributed consensus for the last few years. In fact, I spent 4 whole years working on a PhD in this area, and my thesis is now available online. I'm mindful of the fact that I stand between yourselves and lunch, so I will try to be brief and interesting. But the problem of distributed consensus, which is the problem of how to reach decisions in distributed systems, is a tricky one. It's famous for being difficult to understand. So if there's anything you don't understand during the talk, the problem is not you, it is the topic. Do feel free to reach out to me by email, have a look on my website, contact me over Twitter, or talk to me in person the old-fashioned way. So we're all here today because we believe in the dream of what distributed systems can provide. We believe that they can be scalable. It's in the name. We believe they can be performant, that they can be reliable, and that they can be consistent. But we're also realistic. We know we can't have our cake and eat it. So these are 2 papers from the 80s. The paper on the left is 100 impossibility results in distributed computing. That's a horrifying title for a paper. Here's 100 things you can't do. End of story. And on the other side, we have one of the most famous papers in computer science, the impossibility of distributed consensus with one faulty process. This is also known as the FLP result. And this says that distributed consensus is impossible in theory. This paper is what founded the area and the research into distributed consensus. So if you have a topic and you want people to spend decades working on your topic, write a paper saying it's impossible, and people will spend a lot of effort trying to prove you wrong. And we see this need for compromise in practice too. So this is a figure that I use to scare my students. This was not done by me. It's included in the survey paper that's linked on the slide. And it gives an overview of the consistency levels that are available in different distributed systems. What we'd love to have in practice is linearizability, that guarantee at the top, that guarantee that everything happens instantaneously and everything appears to have happened in basically a total order. Our distributed system looks like it's not distributed at all. But we can't always have that. That comes with availability problems, it comes with performance problems, and so we've invented all of these other consistency guarantees that can provide us with better fault tolerance and better performance. But what I would really love to do, because I can't understand what's going on here, is to get that linearizability, to get that strong guarantee at the top, and just to reduce its cost. And that is the subject of today's talk. Distributed consensus, as we're going to define it today, is simply the problem of deciding a single value. There are 2 components in the system: servers, which store the value, and clients, which propose values and learn which of their values was decided. This is not a talk about blockchain. We assume that the system is non-Byzantine. That means that the participants in our system do as they're told. They don't act arbitrarily, and they're not malicious. What makes this seemingly simple problem, in fact very difficult, is the requirements that we have for a consensus algorithm. Firstly, we require safety. We require that all clients learn the same decided value. What makes this difficult is the fact that we require this even if the system is unreliable. So if our servers fail, if our clients fail. And we require this if our system is asynchronous. So we can't assume that our clocks are synchronized, we can't assume a bound on how long it takes for a message to be delivered, or even if that message is in fact delivered. And secondly, we want to provide progress. So we want to say eventually all clients must learn a decided value. The second guaranteed progress does allow for you to make some assumptions regarding synchrony and reliability, because it's impossible to do it without making any assumptions. That's what the FLP result said. So there's one algorithm that is synonymous with distributed consensus. This is the Paxos algorithm. It was originally proposed in this paper, Part-Time Parliament, by Turing Award winner Leslie Lamport. It took about 10 years to get this paper published, so it actually came out in the 80s. So there was a large body of work referring to this paper before this paper was even published itself. If you've used Zookeeper, that uses a protocol underneath called ZAB to provide atomic broadcast. That shares most of its foundation with Paxos. If you've used etcd, that's based on Raft, and Raft is itself based on Paxos. In fact, basically all of the consensus algorithms that we see deployed in practice are based on Paxos, based on this one big algorithm. This algorithm achieves consensus in 2 phases, and each of those phases requires a majority of servers to participate. So let's see what people have to say about this algorithm. Leslie Lamport, the inventor of the algorithm, says, the Paxos algorithm is very simple. That's great. This algorithm follows almost unavoidably from the properties we want to satisfy. Like, if you think about consensus, you would just derive Paxos for yourself. You just fall over it. You couldn't help it. Let's see what engineers have to say about this. There are significant gaps between the description of Paxos, the Paxos algorithm, and the needs of a real-world system. And it's not just engineers who are struggling with this. Also, researchers in the field of systems do too. So in the Raft paper, they say, we concluded that Paxos does not provide a good foundation for building systems or for education. It's clear that there's a substantial issue when it comes to the subtlety and the understandability of the Paxos algorithm. For me, this is just one of the 2 main limitations of Paxos. The second limitation is performance. Paxos is slow. That's why in systems we reserve consensus usually just for our most important operations, so for coordination and for orchestration services, instead of putting it in the critical path of our systems. Paxos is slow because each decision requires 2 phases with the majority of participants. Many people will tell you that that cost is inherent in solving the problem of consensus. I'm going to hope to try to convince you today that that is not the case. So in today's talk, we're going to rethink the underlying principles of consensus. I'm going to reframe the problem of consensus using immutable state. In this case, write once registers. The great feature of immutability is that we know that once something's been set, it never changes, and that makes it a lot easier to reason about what happens in an asynchronous system. In the next part of this talk, I'm going to describe this famously difficult algorithm for you and show that it is in fact conservative. I'm just going to talk about one of the ways that it's conservative, which is how it uses quorums, but in my research work, I've talked about all different ways. And in the third part, I'm going to show you an algorithm. I call this algorithm All Aboard Consensus, and it seeks to achieve consensus in just 1 round trip. So let's begin with a distributed consensus with write once registers. If we have a single server, reaching consensus is trivial. This server has a register, client comes along, proposes a value, the server stores that value and responds to the client. That value, in this case A, is decided. Another client comes along, they propose a different value. Unfortunately, the value is already decided, so the client learns that the decided value was A. However, if we then try to scale this up to having multiple servers, because we'd like to have some fault tolerance, things can quickly fall apart. So for example, we may have a system where some clients have their register written to one value, and other clients have their register written to another value. So in order to construct a consensus algorithm, we need to have multiple registers on each server. And to save me spending a lot of time drawing out these figures, we're going to use a state table to represent the state of the servers. So each column is the state of one of the servers, and each row is the kind of register on that server. And we also have a special nil value. The purpose of this nil value will become apparent later, but it basically allows us to write to a register and block it from being written to by anybody else. So we have a setup where clients can come and read and write to registers. But when does a client know that a decision has been reached? We say that a value has been decided when it's been written to the same register on a subset of servers known as a quorum. At this point in time, I don't want you to assume that there's any intersection requirements between quorums if you're familiar already with consensus algorithms. A quorum is just a subset of servers. It can contain one server, 20 servers, every server, it doesn't matter. Once a client reads a value from a quorum, it learns that that value has been decided. And we can represent the quorums of a system using a simple table. So we've got the registers. In this case, all registers use majority quorums in a system of 3 servers. And here's an example of a state table. Here we see that a decision has been reached in register R0, and a decision has again been reached in register R2. Here's a different example of a quorum table. Here we have the quorums varying depending on the register sets. So for register 0, the quorum of these 4 servers is all the servers. And then for register 1 onwards, the quorums are either the first 2 servers or the second 2 servers. And here again is an example state table. So we can see a value's been decided at R1 and a value's been decided at R2. As you'll probably observe, we haven't really achieved anything yet. We can still just decide multiple values, and so we don't even have the safety property that we wanted to have. So in this example, at register R1, we've decided 2 different values. We've decided the value C and the value A. In this other example, we've decided 3 different values, the value A, B, and C at register R0, R1, and R2. So we're going to need to do a little bit more work to ensure safety. Our safety criteria is that only one value should ever be decided by the system. So that means that multiple quorums can decide values. Those values just have to be the same value. It's useful to allow this in practice because it means that we can tolerate failures of servers. So we're going to make it the responsibility of the clients to ensure that what they're doing is safe before they do it. So before a client writes to a register I, it must ensure that no other values are decided for the registers 0 to I. Inductively, that means that we'll never end up with 2 different decisions. So now we're going to take a look at how Paxos achieves this. So as I said before, Paxos is a 2-phase algorithm that's based on majorities and solves distributed consensus. Paxos is usually talked about, as I said, in terms of majorities, although it can use any intersecting quorum. So this is an example of what the quorum table might look like. Again, we're just using majorities, so any 2 servers of 3. We can split our safety requirement up into 2 parts. So before a client writes a value to a register I, it must ensure, firstly, that no other values are decided in the same set of registers, and secondly, that no other values are decided in any of the previous registers. So we'll deal with the first one first. Paxos solves this using the register allocation rule. This means that registers are allocated in a round-robin fashion to clients, and clients can write at most one value to each of the allocated registers. This ensures that at most one value is written to any set of registers, and therefore at most one value is ever decided by any set of registers. So that solves the first criteria, it's the easier of the 2. Now we'll have a look at how a client can ensure that no previous decisions have been reached. A client can achieve this by reading one register from each of the quorums of the previous register sets, and it needs to ensure that none of those registers are unwritten, and if it finds unwritten registers, as we'll see, it writes nil to them. And if any registers do contain values, that client must write the value from the greatest register. Together, these conditions ensure that if a client writes a value and that value subsequently becomes decided, that value will be the same as any previous decisions. So that's dealt with the second criteria. So we're going to have a quick look into the details of the Paxos algorithm. If this doesn't make sense first time, don't worry about it. The overall idea is that would be good to take away is that it uses 2 phases. The first one ensures that it's safe to write a value to registers, and the second phase writes that value to the registers. So this is the first phase where a client chooses which register it's going to attempt to make a decision in, and it contacts the servers about that register. When the servers receive the message from the client, they write nil to any unwritten previous registers. This writing of nil is really important because it basically freezes the system. It basically freezes the state of that quorum and stops it from changing in the future. And the server, also responds with the greatest value in their registers. In the second phase of the algorithm, once the majority of servers has responded, a client chooses the greatest value that it received in the first phase and goes on to write that into the registers. Again, this proceeds similar to the first phase. When a server receives a request from a client, assuming the register is unwritten, the client writes nil into any of those empty registers and writes the value into the register I as requested. The servers then respond with accept, which is like the I've done the work for you message. And when a client receives a response from the majority of servers, it can safely terminate having learned the decided value. So a quick example here. The details aren't super important, but mostly just this phase one is doing the legwork for safety. So a client comes along, sends the prepare message to the servers. The servers write nil to their register R0 and respond with promise 1. And then the client goes through the second phase of the protocol, telling the servers write value A into register 1. These servers obey and respond positively to the client. Another client comes along. This time they're trying to use register 2. They send their message to the servers, but their servers don't need to make any changes. And they respond with the greatest value and register number that they have. And then this client proceeds again as before, asking the servers to write a particular value, in this case A, to register 2. And then it's done successfully. The details of this aren't like super important for now. It's just the first phase is ensuring safety, and the second phase is when you're actually doing the legwork of writing values into registers. So Paxos requires its quorums to all intersect. It doesn't matter if a client is using this quorum for the first phase of the algorithm or the second phase of the algorithm. It doesn't matter if the client is writing into register 0 or writing into register 200. Paxos simply requires that all quorums intersect. The research that we've done on this and shows, in fact, that this is way more conservative than it needs to be. In practice, the only requirement here is that a client who's writing into register I during their first phase needs to get agreement from at least one server from the quorums for the previous registers. So that means, for example, if a client has register 0 and is trying to write into register 0, there actually is no quorum intersection requirement. They can just write straight into that register and skip the first phase of the protocol. So now we're going to put this to work. As I said before, classic Paxos is a two-phase algorithm that allows any client to reach agreement. In practice, systems like Raft and Zookeeper use a form of Paxos known as multi-Paxos. This is where one of the clients completes the first phase and is then able to reach consensus in just one round trip. The problem is that only that one client is able to do this. So that one client, known as like the leader or the master or the primary, is responsible for all the work in the system. In terms of latency, that means you have to forward all the decisions through this single centralized point, and it then bottlenecks the throughput and performance of the system. What would be amazing is if we could have an algorithm that could achieve consensus in just one round trip and that any client could do. Nothing comes for free in distributed systems. So in order to build this algorithm, we're going to use these two other facts. We're going to use the fact that in systems, it's often the case that a server and client are co-located on each participant. So that means that one of each client is able to access the state of one server for free without even traversing the network. And secondly, we're going to use the fact that failures are rare. We do and we will continue to tolerate the failures of the minority of servers, but that isn't going to occur that often. Most of the time, everything's going to be up and everything's going to be working well. So here's an example of what a quorum table might look like. Here we're using 3 servers, and because we've co-located them with clients, 3 clients. The first 3 registers use a quorum containing all servers. And then the registers from 3 onwards just use majority quorums, the same as Paxos. The implication of this is that a client in the system now has 2 options for how to reach consensus. They can take the fast path. This means they're using registers as register 0, 1, or 2. They can do their first phase of the algorithm locally and do the second phase of the algorithm with all 3 servers in the system. This allows them to achieve consensus in just 1 round trip. However, this won't always be successful. Perhaps one of those servers has failed, in which case a client can fall back to the slow path. The slow path is the classic Paxos algorithm. The advantage of this algorithm is that if all the servers are up, we can now achieve consensus in just 1 round trip from any client in the system. The disadvantages are that it does require co-location and that 2 round trips will be needed if one of the servers is slow or unreliable. This algorithm is just the beginning. I wrote a paper on the quorum intersection for consensus, known as flexible Paxos. There's also another paper on using write-once registers. And if 2 academic papers isn't enough reading, I have a 150-page PhD thesis that you can read about the topic. What I've shown you today is just one example algorithm. In fact, there are many, many different algorithms for consensus. It's not the case that there's one algorithm that's better than Paxos in every way and in every scenario. There's no silver bullet here, and nothing comes for free. But when it comes to distributed systems, whilst trade-offs are inevitable, you can choose the trade-offs that you make. I believe in many cases an algorithm such as all-aboard consensus would be a better fit than Paxos. And there are many other algorithms that would be better fits than all-aboard consensus in different scenarios. So Paxos, to conclude, Paxos is just a single point on the broad spectrum of possible solutions to consensus. If you're looking to solve consensus in your distributed system, you don't have to use Paxos. There are loads of different options out there. Thank you very much.